Okay, so today is the second day we are going to talk about parametric equations. In particular, today we are going to talk about how we can rewrite parametric equations into rectangular form, which is the form that you guys have been so used to using in terms of just x and y, and how do we do that? And the first thing we want to know is that when we are rewriting these parametric equations into rectangular form, we are essentially going to be eliminating the parameter. Okay, so when translating or rewriting parametric equations in rectangular form, we are eliminating the parameter. Now, you might be wondering to yourself, well, if you can convert it into rectangular form, then what's the point of having something in parametric form? So in parametric form, uh, we are able to determine speed and direction, whereas in rectangular form, we are not. However, rectangular form can be useful, particularly when it might be difficult to draw what the curve is, or it can just make it a little easier to figure out what it looks like. So just note that converting into rectangular form is only a tool to help draw the curve. Parametric form is still necessary to determine the speed and direction. So how do you go about actually eliminating the parameter? How do you actually go about converting something into rectangular form? So 3 basic steps anytime you are trying to eliminate the parameter. These are general steps. We will do an example at the end where we actually won't be using these particular basic steps, but we'll get into that when we get there. In general, you'll want to solve for t in one of the parametric equations. It doesn't matter which one you choose. I like to choose the one where it's easiest to get t by itself. Once you have that, then you are going to substitute for t in the other equation, right? So now you've solved for t in one of them, so you have t equals something. So now you're going to do a substitution into the other equation. And that way now you just have an equation that's in terms of x and y. If you can simplify, then simplify. Okay, so we're going to do an example, and we're going to go through these 3 steps. We're going to kind of look and see in which case will it be easier to solve for t, kind of make that decision, but just know that you can go about doing these problems in a different way, solving for t in the other equation and then substituting into the other one. So example 1, convert the following parametric equations into rectangular form. We have x equals t squared minus 4 and y equals 1/2 t, right? So this is clearly in parametric form. We have x equals something in terms of t, y equals something in terms of t. Okay, so if you're taking a look at both of these, you want to determine which one will it be easier to solve for t in. Now you can technically solve for t in either of them, right? For the first one, you can add 4, take the square root of both sides, you'll have plus or minus. In the second one, you can multiply both sides by 2, and you'll end up with t equals 2y. So it looks like the second one will be easier. We don't have to deal with the square root, we don't have to deal with a plus or minus in there. So let's go ahead and solve for t in the second equation. Okay, so multiplying both sides by 2, we end up with 2y equals t. That's the first step. Second step, now we are going to substitute t in the first equation. So instead of writing t squared minus 4, we are going to write in 2y squared minus 4. So notice when we do that substitution, that parameter t is now gone. We've eliminated the parameter. Right, so x equals 2y in parentheses squared minus 4. Looks like this is something we can simplify, so that's the third step. Go ahead and simplify, so we have x equals 4y squared minus 4. Okay, and that is those 2 parametric equations in rectangular form. So you can see how having just getting from parametric equations to rectangular form, in rectangular form you only have 1 equation, parametric equations you have to have 2 equations, but if you have it in parametric form, you'll be able to say the direction in which this curve travels, versus in rectangular form, you actually don't know and you can't tell from this equation how this curve is going to travel. All right, let's take a look at another example. Let's do something a little bit more complicated. We have x equals 1 over the square root of t plus 1, and y equals t over t plus 1. Okay, so if we're trying to think about which one might be easier, in this particular case, there might not necessarily be one that's easier than the other. You'll notice in the first one, we've got a square root in there. Maybe we don't want to deal with that. In the second one, you'll also notice that there's no square root, but t shows up in both the numerator and the denominator on the right-hand side. So that might also make it more complicated. So if you're not sure which one might be easier, then just pick one. So let's start with the x equals equation, and we'll try to get t by itself in that equation. So the first thing I'm going to do is I'm going to square both sides. So we have x squared equals 1 over t plus 1. And let's get rid of the fraction. We definitely need that t in the numerator. So multiply both sides by t plus 1. And I'm going to go ahead and distribute the x squared. So x squared t plus x squared equals 1. Now remember, we're trying to get that t by itself, so I'm going to subtract x squared from both sides. And it looks like divide both sides by x squared. So we have t equals 1 minus x squared all over x squared. Okay, so we successfully got t by itself. So second step is to substitute for t in the second equation, which in this case is the y equals equation. So we are going to have 1 minus x squared over x squared in the numerator. In the denominator, 1 minus x squared over x squared plus 1. Okay, so I know this looks really complex right now, but that's where simplifying this will actually help us. So if we multiply, so we're trying to get rid of those fractions within fractions, right? So to do that, let's multiply the top and the bottom by x squared. So on the top, the x squared and the x squared in the denominator will cancel, leaving us with 1 minus x squared in the numerator. And on the bottom, that 1 minus x squared over x squared, again, the x squared and the x squared cancel. You're left with 1 minus x squared, but we also have to multiply that 1 that was not part of a fraction, the plus 1 there, multiply that by x squared, so we end up with plus x squared. Now you'll notice the minus x squared and the plus x squared end up canceling. So we actually just have 1 minus x squared all over 1. And anything divided by 1 is just itself. So we actually just have the equation y equals 1 minus x squared. Now, remember, the point of converting something from parametric form into rectangular form is to help us figure out the shape of the graph, right? If you looked at the parametric form here, x equals 1 over square root of t plus 1 and y equals t over t plus 1, you might not be able to figure out what the shape of the graph looks right away. Now you can obviously plug in values of t in order to help you figure out what the shape of the graph is, but this might actually be not too bad. So think about y equals 1 minus x squared. What is that graph going to look like? Well, it's x squared, so we know it's a parabola. There's a minus in front of the x squared, so it's facing down. And there's a 1, so we're going to shift the entire thing up 1. So pretty easily, we can get what the shape of this graph looks like. It's just a parabola facing down, shifted up by 1. Now, having the parametric form again is still useful because that will help us determine which direction in which the graph is going. So in this case, we don't know if it's going from left to right or right to left, and so having the parametric equations there will help us determine that. Okay, now I mentioned before that we were going to go over a case in which we weren't going to necessarily use those 3 general steps of first solving for t in one equation, plugging into the second equation, and then simplify. So the particular case I'm talking about is when you're using trig. So for equations with trig, you're going to use the trig identity sine squared plus cosine squared equals 1. Now for our purposes, we're just going to have parametric equations in terms of sine or cosine, but just know that you could use any of the trig identities to help you substitute in there and be able to eliminate the parameter. So if we take a look at example 3, we have x equals 3 cosine theta, y equals 4 sine theta. Now theta in this case is your t, is your parameter. So this is not something where you're going to really want to solve for your parameter. You'll end up with, for example, if you took the first one there, you'd end up with theta equals cosine inverse, and you don't want to have to end up plugging that into the second equation. You'll be taking sine of something something cosine inverse. That's actually going to make it more complicated and not actually help you figure out what the graph will look like, which is the point of converting parametric equations into rectangular form. So what you do want to do though is you want to get the trig function by itself. So in this case, x equals 3 cosine theta, get cosine theta by itself. Y equals 4 sine theta, get sine theta by itself. So divide, in the first equation, divide both sides by 3. In the second equation, divide both sides by 4. So we have x over 3 equals cosine theta, y over 4 equals sine theta. And then all you have to do is use the trig identity sine squared theta plus cosine squared theta equals 1. And now substitute in to this equation, right? We're trying to eliminate the parameter theta. So we're going to substitute for sine theta with y over 4 and substitute cosine theta for x over 3. Now notice theta is now completely gone. So we have successfully eliminated the parameter. Now, what does this graph look like? This you might have to kind of dig back into your Algebra 2 knowledge, where you did some work with some ellipses maybe. So just as a reminder, an ellipse is of the form here, x minus h squared over a squared plus y minus k squared all over b squared equals 1. And so what we have here, well, since we don't have an h or a k value, it's pretty clear for this particular problem that this is going to be centered at 0, 0. And then the a and the b, we can call them the quote-unquote radius. They're not actually the radius because an ellipse is not a circle, but it extends from the center in the horizontal direction by a and in the vertical direction by b. So in this particular case, in our equation, just be very careful. In our equation, we just have our x and y flipped, right? We have the y term first and then the x term. So in our case here, we have x over 3 squared, the whole thing is being squared. So in this case, our horizontal quote-unquote radius is going to be 3. Why is it 3 and not square root of 3? Well, because it's the whole thing being squared right now. Right, so this is really the same as x squared over 3 squared. So a is 3. And then same with y. So the y squared over 4 squared tells us that the vertical quote-unquote radius is going to equal 4. So that means in the horizontal direction, the ellipse is going to go out by 3. In the vertical direction, it's going to go out by 4. So it is lengthwise, the longer side of the ellipse is going to be along the y-axis. Okay, and that's all we have for today.